Hey everyone, and welcome to this explainer. Today we're taking a seriously fascinating journey, starting all the way down at the microscopic level of a single processor core and zooming all the way out to those massive, room-sized server architectures you hear so much about. If you've ever found yourself wondering how the underlying hardware actually works to power this massive AI revolution, and why certain chips literally cost as much as a luxury car, well, you're in the exact right place. We are going to break down the silicon.
Here is our quick roadmap for today. We're going to kick things off with the fundamental difference between standard processors and graphics processors. Then we'll dive right into the silicon to explore streaming multiprocessors, unpack a really cool hardware paradox comparing core counts to clock speeds, and finally, we'll zoom out to see how data centers scale the whole shebang up with NVLink. All right, let's jump right in. Section 1, the core difference, sequential versus parallel computing. Okay, let's dive into this. Why exactly does AI need a completely different brain to function? I mean, why can't it just use what we already have? Well, to answer that, we really have to look at traditional processors. The CPUs running the operating systems on the laptop or phone you're using right now were designed to be incredibly fast at doing one highly complex thing at a time. But modern workloads, stuff like deep learning and massive 3D rendering, they're fundamentally different beasts. They don't need to solve one extremely complex math problem sequentially. Instead, they need to calculate millions, literally millions, of simpler math problems all at the exact same time. This setup brilliantly illustrates that architectural divide. Think of a standard CPU as a tiny group of highly brilliant professors. They're incredibly fast, operating at speeds of around 3 to 4 gigahertz, and they've got access to a large cache of memory per ALU, or arithmetic logic unit. They're absolutely perfect for complex sequential tasks where step B strictly depends on step A. But then, instead of a few professors, imagine a GPU as thousands of eager students working together in parallel. Now, they operate at a slower clock speed, roughly around 1.2 gigahertz, and they have way smaller memory caches per core. Individually, a single GPU core just isn't as capable as a CPU core, but when you have thousands of them executing independent instructions side by side, their combined throughput is absolutely staggering. Moving right along to Section 2. Inside streaming multiprocessors or the microcluster. Let's zoom in past the overall GPU chip directly into its building blocks. So a huge misconception a lot of people have is that a GPU is just this giant flat sea of identical generic cores. But actually, scratch that. It's way more organized than that. Enter the SM, or streaming multiprocessor. An SM is definitely not just one generic core. It's a self-contained execution block inside the GPU that acts like its own miniature processing cluster. It even has its own super fast local storage, like an L1 cache, which means the memory is kept right next to the cores doing the actual work. Think of it as a complex, highly organized neighborhood of compute resources. Let's look a little closer at what's inside this neighborhood, because having different, specialized units for different math problems is the secret sauce that makes a GPU so efficient. First up, you've got your load and store units, the LDSTs. These guys are constantly doing the heavy lifting, moving data back and forth between memory and registers, so the processors always have the numbers they need exactly when they need them. Then we have the tensor cores. If you're into AI, these are the absolute stars of the show. They are specialized hardware units designed exclusively for dense matrix operations, specifically the multiply-accumulate workloads that are basically the backbone of deep learning. And finally, we have the SFUs, or special function units. These step in for the really complex, specific math, stuff like calculating logarithms, exponentials, or reciprocal functions. It's this exact mix of specialized resources all firing off in parallel inside the SM that gives a GPU its power. All right, part 3, core count versus clock speed. Let's transition to the macro level of the chip to see how these SMs are balanced in the real world. This brings us to a really fascinating hardware mystery. I like to call it the RTX 3090 versus A100 paradox. We're comparing a high-end consumer gaming card, the RTX 3090, to an absolute data center titan, the A100. And what's wild here is that both of these GPUs are built on the exact same underlying silicon die. They both use NVIDIA's GA100 chip and share the exact same Ampere architecture foundation, yet they are tuned for completely different universes. Now, what's really interesting about this is that if you just glance at the raw numbers, the consumer-focused RTX 3090 surprisingly seems to win. It has significantly more CUDA cores, almost 10,500 compared to the A100's roughly 6,900. It boasts a faster boost clock at 1695 MHz, and it even has a higher FP32 throughput at over 35 teraflops. So, on paper, for traditional metrics, the gaming card looks like it's totally beating the high-performance data center giant.
But here is the massive plot twist. The moment we shift our focus to FP16 performance, which is the half-precision format absolutely critical for training AI models, the A100 completely crushes the 3090. Despite having fewer general cores and a slower clock speed, the A100 delivers a staggering 312 teraflops of FP16 throughput compared to the 3090's 35.6. Guys, that is a 778% performance increase in AI critical throughput. How on earth is that possible?
Well, it all comes down to architectural synergy. Pure speed and huge core counts mean absolutely nothing without the right setup for the specific workload. The A100 dominates AI because it features superior mixed precision optimization. Remember those tensor cores we just talked about? The A100 packs 432 specialized third-generation tensor cores. But honestly, the biggest game changer is its extreme memory bandwidth. The A100 uses specialized HBM2E memory, achieving up to 1,935 gigabytes per second of bandwidth. To put that in perspective, it's an absolute fire hose of data. The 3090 is fast for gaming, sure, but it simply can't feed data to its cores fast enough for massive AI models. The big takeaway? Architecture, specialized cores, and massive memory pipelines are what truly win the race in the data center. Finally, let's wrap up with Section 4, Scaling Up with NVLink. What happens when one ultra-powerful GPU still isn't enough?
This is the point where physical connections become your biggest bottleneck. Traditionally, a GPU connects using PCI. You can think of PCI as the standard shared motherboard highway. It's broadly compatible, and it's great for general data movement. But when you're training a massive AI model, multiple GPUs need to constantly swap huge amounts of intermediate data. If they try to send all this massive data over that standard PCI highway, it's going to cause a major traffic jam. And your incredibly expensive GPUs will literally just sit there idle waiting for data. Enter NVLink. NVLink is a private, high-speed express lane directly between the GPUs. It bypasses the shared motherboard entirely, letting GPUs exchange massive amounts of data directly with way higher bandwidth and super low latency.
Let's move to and see how this builds, because engineers have to scale this infrastructure up logically. Step 1 is standard PCIe. Doing general compute or gaming on a single GPU, PCIe is completely fine. Step 2 is NVLink. Once you have a small cluster of GPUs working on a shared model and they hit a communication bottleneck, you use NVLink for direct, high-bandwidth sharing between them. But what if you're building a massive supercomputer? That requires Step 3, NVS switch. NVS switch takes the NVLink concept and acts as a massive scaling layer. It allows huge pools of dozens or even hundreds of GPUs to communicate and share memory seamlessly. It makes them function almost like one giant, unified brain. Which brings us to the ultimate question we have to ask ourselves today. As AI models continue to grow exponentially, pushing well into the trillions of parameters, where will our real bottlenecks lie? Is the future of high-performance hardware actually about building faster individual processor cores? Or is the true challenge simply building faster, wider highways between them, so those cores never starve for data? It's a massive engineering puzzle that will absolutely dictate the next decade of compute. Thanks so much for joining me on this explainer. I hope this helped map out the incredibly complex architecture powering the AI revolution.